Okay, these are the topics today. Before I present the topics, take a review about some key points from the last class. Review number one. Suppose we have some vectors. Let V1, V2, Vk be some vectors. There are many ways to combine these vectors, but the following one is called a linear combination. A linear combination, a linear combination of the vectors is some number, some scalar times V1 plus a scalar times V2. Scalar times Vk. Combine these vectors in this way is called a linear combination, where C1, C2, Ck are scalars. Review number two, a set spanned by some vectors. Again, let V1, V2, Vk be vectors. Then I use the following notation. To denote this set, the set of all possible linear combinations of these vectors. Put all the linear combinations of these k vectors together. We have a set. The notation is this notation. We call this set. We call this set the set spanned by these k vectors. Review number three. A times V, a matrix times a vector. There are two formulas. Formula one, okay. Write matrix A into columns. Cut matrix A in columns. First column is a vector. Let me denote the vector by A1, A2. Second column. Suppose the matrix has n columns. And then vector V. Vector V should have n entries. The number of entries in vector V should be equal to the number of columns in the matrix A. Otherwise, A times V is not computable. V1, V2, Vn. V1, V2, Vn, they are numbers. There are two formulas. to compute A times V. The first formula is A times V. It is a vector. Which vector? A linear combination of the columns of the matrix A. Scalar V1 times vector A1 plus scalar V2 times vector V2 and scalar Vn. Scalar, this is scalar log a vector. Vn times the last column. Yeah. A matrix times a vector is a vector. Linear combination of the columns of a matrix A. Formula 1. Second formula. A times V. It is a vector. The ith entry of the vector is equal to row I of matrix A times vector V. Row I of matrix A, it is AI1. AI1 is the first entry on row I. AI2, second entry, and AIN, because the matrix A has n columns, so AIN times the vector V1, V2, Vn. The meaning of row I times the vector is the sum of the products of the corresponding entries. That means that first entry times first entry plus second entry I2 times second entry and so on. Last entry times last entry. Two formulas to compute a matrix times a vector. Review C. Review D. A linear system can be written as a vector equation, also as a matrix equation. A linear system, let me save some writing. I only write down the augmented matrix. A linear system, suppose whose augmented matrix is this, okay? Coefficient matrix, the first column A1, second column A2, AN. Then separate from the right side. The right side is vector B. A linear system can be written as a vector equation. Which vector equation? This vector equation. X1 unknown times first column, X2 unknown times second column, Xn last column is equal to B. Okay. Further, the left side of the vector equation actually is a matrix times a vector. Okay. Further, let matrix A form a matrix A. First column A1, second column A2, last column AN. Actually, this matrix A is the coefficient part of the augmented matrix. And X, this vector, is the vector of the unknowns, x1, x2, xn. Then let me call this vector equation number 1. Then equation number 1 is, by the definition of a matrix times a vector, the left side of this equation is A times X is equal to B. So a linear system can be written as a vector equation as a matrix equation. The reverse is also true. A matrix equation is a vector equation and also is a linear system. This is a review about the key points from the last class. Okay, now today's topic. Number 1, I want to show you more examples about section 1.4. More examples. Take a look. At the following examples. Example 1. Under this topic, let A be this matrix. And B be this vector. Okay, now the question is the equation A times X is equal to B. This is a linear system. Is the equation consistent? Consistent means the equation has at least one solution. For all possible B1, B2, B3. Yeah, I want to answer this question. Solution. Yeah. Hey, this is a matrix equation. It can be written as a linear system. The linear system is, okay, the equation AX is equal to B is the following linear system. By formula for a matrix times a vector, the row vector formula. Okay. This is a vector. The first entry of this vector is row 1 times the vector X. It is row 1 times the vector X is first entry times first entry, X1. Second entry times second entry. Then third entry times the third entry. This is the first entry of the left side of this equation. First entry should be equal to the first entry of B. So one equation. Second equation. Second entry of A times B, A times X, this vector is row 2 times X. First entry times X1 plus second entry times X2 minus third entry times X3 is equal to the second entry of vector B. B2. Now the third entry of A times X is row 3 times the vector X. Is equal to the third entry of the right side, B3. So, see, this matrix equation is this linear system. Now, to answer whether the linear system consistent for all possible B, solve the linear system. Okay. Now solve the linear system. How to solve? Augmented matrix. Coefficient matrix. Actually, coefficient matrix is matrix A. Then right hand side. Second equation is right hand side. Third equation, right hand side, then separate augmented matrix. Now I reduce the augmented matrix to epsilon form by forward elimination. Okay, then let me write my solution on a new page. Okay, I perform a sequence of row operations. I skip the detail. Okay, so I use this tilde rotation to skip the detail. Tilde means this matrix reduce the matrix by a sequence of row operations. Then I get epsilon form. It is 1, 3, 4. B 0, 1, 4, 10. B2 plus 4, B1. 0, 0, 0. B1 minus 1 half B2, B3. Okay, now I can answer whether or not the linear system is consistent for arbitrary B1, B2, and B3. Look at the bottom non-zero row. Yeah, this row, non-zero. Whenever one entry in the row is non-zero, then that row is considered non-zero. This row is the following equation. Okay, this row is 0 times x1 plus 0 times x2 plus 0 times x3 is equal to this. Now, ask yourself whether or not this equation has a solution for arbitrary B1, B2, and B3. The answer is no. For some B1, B2, B3, this equation has no solution. When the right side is non-zero, this equation has no solution. For example, if I take B1 is 1, B2 is 1, B3 is 1, then this equation is 0 times x1 plus 0 times x2, 0 times x3 is equal to 1 minus 1 half, 1 half. It is a 3 half. No solution, no solution. So the answer to this question is, the equation consistent for arbitrary B1, B2, and B3? The answer is no. 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 Because this matrix, okay, this matrix, the third row the third row is not a pivot row. The third row contains low pivot number. That's the reason. Yeah. You see, after I reduce A to epsilon form, you see the third row all are zeros, low pivot number. Therefore, linear system is not consistent for arbitrary A, B, and C. Okay. In other words, actually, I can answer this question in a different point of view. Okay. Because the linear system, okay, is a vector equation. X1 times first column plus X2 times second column plus X3 third column is B. Yeah, it's B. Yeah, it's B. Okay, now this vector equation has no solution for some B. We say that column 1, column 2, column n cannot span R3 because vector B is from R3. Some vector of R3, some vector in R3 is not a linear combination of the columns of the matrix. So the columns of this matrix cannot span R3, cannot span the whole space R3. The columns of this matrix can only span a plane or a line, not the whole space R3. Yeah, this is I answer the question in a different view, in the view of spanning. Okay. And also from this example, we can see the following theorem. Okay. Yeah, actually, the following theorem is motivated by this example. Theorem. And let A be an M by N matrix. Okay. M and N may not be equal. So this matrix is a rectangular matrix. Then the following statements are equivalent. What it means? The following statements are equivalent. That means that either they are all true or they are all false. That's what equivalent means. If one statement is true, other statements are also true. If one statement is false, other statements are false. Number 1. Okay, statement 1. For every vector B in ROM, yes, ROM, okay. AX is equal to B. Okay, because A has M rows, so A times X is a vector in Rm. So B should be in Rm. For every B in Rm, the equation AX is equal to B has a solution. Okay. Statement 1. Statement 2. The coefficient matrix A should have a pivot position in every row. In the previous example, the coefficient matrix not every row in this coefficient matrix has a pivot number. Row 3 doesn't have a pivot number. Therefore, this linear system in this example has no solution for all vector B. Okay. So this linear system has a solution for all vector B, then each row should contain a pivot position. Here, let me emphasize that coefficient matrix, okay? Each row of the coefficient matrix, not augmented matrix. Okay. Yeah, this theorem actually is from example 1. Example 1. Okay. Example. Now, second example. Example 2. Let matrix A be 1, 3, 0, 3. Negative 1, 1, 0, 2, negative 8, 2, 0, 3, negative 1. A 4x4 matrix. Now, questions. How many rows of this matrix contain a pivot contain a pivot position. Okay. Then answer the following question. Does the equation AX is equal to B have a solution for all vector B in R3? Okay. Second equation. We can answer the second equation by this theorem. Okay. Now, let me answer the first question. Given us a matrix, how many rows of the matrix contain pivot positions? How to answer this question? Reduce the matrix to epsilon form. Okay. Reduce the matrix to epsilon form. Yeah. Let me write solution here. Matrix A. Now perform row operations, then I get epsilon form 1, 3, 0, 3, 0, 2, -1, 4, 0, 0, 0, 5, 0, 0, 0, 0. Now I can tell which position is a pivot position. 1, 1 position is a pivot position. So let me mark down in the original matrix. Yeah, this position, pivot position. This position is a pivot. So 2, 2, the location 2, 2 is a pivot. This a pivot number. So 3, 4, this location is a pivot location. So the answer to the first question, how many rows contain a pivot position? The answer is 3 rows. 3 rows. Okay, now second question. Does the equation has a solution for all B? The answer is row, because it's filled. Coefficient matrix A has a pivot position in every row, but not in this example, not in every row. Row 3 contains no pivot position. Therefore, by theorem, this linear system has no solution for some vector B. In other words, the columns of matrix A doesn't span the space R3, only span a plane in R3. This is topic 1. Topic 1. More examples about.
I have a question real quick.
Okay, what is your question?
So is it supposed to be R4 instead of R3 because we have a 4 rows?
Correct. Sorry, here. Should be R4, not R3. Good question. Thank you. Yes.
Thank you.
Yeah. And also some okay. If a pivot position, someone asked me a question by check. When will the first example be? What do you mean? When will the first example be? If a pivot position is in every row, but not every column, the statement still true. Yeah. Every row contains a pivot position, then this linear system has a solution for all B. Okay. When the case is a rectangular coefficient matrix, the number of rows less than the number of columns. Some columns contains low pivot position, but it doesn't matter. We require only each row contains a pivot position. Then the linear system has solution for arbitrary B. We don't require all columns contains pivot position. Okay. Second topic. Let me see. Homogeneous linear system. Topic 2. Homogeneous linear systems. Okay. What means homogeneous linear system? Okay. Yeah. A is equal to B, a linear system. Okay. If the right side B is a zero vector, then the linear system, the system is called a homogeneous linear system. If the right side is not equal to zero, that means that if at least one entry in vector B is non-zero, then the linear system is called non-homogeneous. Okay. One thing, this thing is easy to be seen. For a homogeneous linear system, okay, zero is a solution. Why? Plugging zero in X. A times zero, of course, is zero. So zero satisfies the equation. Zero is a solution. So homogeneous linear system is always consistent. Or you can, okay, you can view homogeneous linear system or is always consistent by reducing augmented matrix to epsilon form. Okay. A second view. Okay. Augmented matrix. Now reduce it to epsilon form. Epsilon form. 0, 0. Right hand side is always 0. Epsilon form. Non-zero. Maybe any number. Okay. Non-zero. Any number. Okay. Okay. So maybe the some bottom rows are 0. Okay. When you reduce the augmented matrix to epsilon form, the bottom non-zero row is not in this form. Which form? 0, 0, 0. But the right side is non-zero. If a linear system, after you reduce it to epsilon form, the bottom non-zero row is a row like this, the linear system has no solution. But for homogeneous linear system, this case never happens. So homogeneous linear system always has a solution. Okay. Take a look at one example. Example 1. Under the second topic, determine if the homogeneous linear system has a non-trivial solution. Yeah, let me explain what it means. Non-trivial solution. Where coefficient matrix is 3, 5, -4, -3, -2, 4, 6. Yeah. Okay. Now let me explain. Non-trivial solution. What it means. In the context of homogeneous linear systems. Okay. We know that every homogeneous linear system has 0 as its solution. 0 is called a trivial solution. Okay. A trivial solution is a term only for homogeneous linear systems. For non-homogeneous linear systems, we don't say that trivial solution. Only in the context of homogeneous linear system, because 0 is always a solution. So 0 is a trivial solution. Then how about non-trivial solution? When a solution is not 0, the solution is non-trivial solution. So actually, this example determines whether the linear system has non-zero solution. Okay, same. Right. Then this is our first question. Now second question. Write its solutions in vector form. Okay. Then describe the solution. This linear system at least has one solution. May have infinitely many solutions. Now count all the solutions in R3. Then what is the graph of the solution? Describe the solution set geometrically. Okay, now let me answer the first question. Determine whether the linear system has non-trivial solution. How? Solve it. Okay. Coefficient matrix together with right hand side. Solve it. Okay. Now I skip the detail. Row reduce augmented matrix to epsilon form. The first column corresponds to the unknown x1. Second column x2. Third column x3. Last column right hand side. First column contains a pivot entry number 3. So this is a basic variable. Second column contains a pivot entry, also number 3. The 2 position is a pivot position. So x2 is also basic. The third column has low pivot position. So the third column, we call it a free column. Therefore, this guy, free. This variable is free. That means that you can arbitrarily assign values to x3. Because there is a free variable, the linear system has infinitely many solutions. Therefore, there are infinitely many non-trivial solutions. Non-trivial solution means a non-zero solution. Okay. Since the answer, okay, there is a free variable. Okay. AX is equal to 0 has not just one, infinitely many, has many non-trivial solutions. All right. This is the answer to the first question. Now, second question. Write its solution in vector form. Now, this time, reduce epsilon form is not enough. Further, reduce the epsilon form to reduce epsilon form. Okay. Epsilon form is not simple enough. Continue to introduce zeros to the epsilon form. Okay. All right. Now, let me continue on a new page. Okay. Now, I reduce this epsilon form to reduce epsilon form. Okay. Okay. Now, further, backward elimination. Then I get reduce epsilon form is 1, 0, negative 4/3, 0, 0, 1, 0, 0, 0, 0, 0, 0. Reduce epsilon form. Now, in equations, yeah, this is on many matrix. First row is this equation. Coefficient of x1 is 1, so x1 minus 4/3 x3 is 0. Right side is 0. Now, second row is this equation. Third row, 0 is 0. Yeah. Remember, x1 basic, x2 basic, x3 is free. Solve this linear system for basic variables in terms of free variables to get general solution. General solution means all solutions. Okay. So the general solution is x1 is 4/3 x3. x2 is 0. Then how about x3? Arbitrary free. All right. Now we are required to write the solution in vector form. Now let me write the solution in vector form. Solution in vector form. Solution is a vector. Okay. This vector is a vector of unknowns, free unknowns. Okay. Now, plug in the first equation in x1. Second equation in x2. x2 is always 0. x3 arbitrary, keep x3. Yeah. Unknown is a scalar. Now, take x3 outside the vector, then x3 times this vector. Let me give a name to this vector. Say, let me call this vector v. So therefore, the general solution in vector form is arbitrary x3 times vector v. Yeah. This is the answer to the second question. Now, third question. Then describe the solution set graphically. The solution set the solution set actually is equal to X free arbitrary. So actually, this is a span V. Span V. Right? Solution set. Right? All the solutions together actually is this set. Right? This set is the set of all possible linear combinations of vector V. Okay, now let me plot all the points in this set. Okay. Should be plot the points in R3. R3. Okay. Now general solution is this. Okay, X3, then times V. What is V? V is 4/3 times 4/3 0, 1. Okay. Now suppose this is R3. The origin is here. Origin is a vector. A vector. A point is considered to be a vector. A vector is a point. Okay. Point and vector, same thing. Okay. This is 0, 0, 0. Yeah, 0, 0. Okay. Now arbitrary. When we say X3 is 0, then we get a 0 vector. Oh, this point is a solution. Okay. When X3 is 1, then V, this vector is a solution. What is V? Say suppose here V. This point is a 4, 3, 0, 1. Yeah. Okay. Yeah. Or you can join these 2 points with an arrow. Yeah. This is a vector V. Okay. Okay. So you can choose X3 -1, then get this point here. Okay, here. Okay. So X3 arbitrarily choose, then plot all the points. You will see a 9. Okay. So all the points together, you will see a 9. A 9. Yeah. This 9 passes origin and is parallel to the arrow for vector V. The arrow for vector V is this arrow starting at origin and ending at this point. This arrow represents vector V. So the line through the origin and parallel to this arrow is the graph of the solution set. Okay, solution set. Yeah. Topic 2. Now topic 3. Topic 3. What is topic 3? Let me. Non-homogeneous linear systems. Right. Topic number 3. Non-homogeneous linear systems. Okay. A linear system. Okay. Is non-homogeneous if the right side is not 0. Non-homogeneous. It turns out that non-homogeneous system and homogeneous system, their solutions have some relation. Right. Yeah, let me write this down. Okay. There are exists a connection between the solution of non-homogeneous linear system, and the solution of its associated homogeneous linear system. What it means? Associate homogeneous system. That means that this system coefficient matrix the same with the coefficient matrix of this linear system, but the right side is 0. Right side is 0. Let me show you one example. Say example 1. Okay. This example is a continuation of the previous example. Okay. That means that I use the coefficient matrix in the previous example. Okay. Okay. Now solve is non-homogeneous linear system where coefficient matrix is the same with, yeah, this is a previous example. Yeah, this is the coefficient matrix. Okay. 3, 5, -4, -3, -2, 4, 6, 1, 8. But the right side is 7, -1, -4. Okay. Now I solve this linear system. Then we will see, yeah, indeed, there is some connection between the solution of this non-homogeneous linear system and the solution of the corresponding homogeneous linear system. Okay. Okay. Now, okay. Solve this linear system. Question 1. Now, second question, the same. Write the solution in vector form. Same questions. Then describe the solution set geometrically, graphically. Okay, now let me answer the first question. Solve the linear system. Then augmented matrix. Okay. All right, solution. Now solve. Coefficient matrix together with right side is augmented matrix. Now coefficient matrix is 3, 4, 5, -4, 3, 2, 4, 6, 1. Yeah. Coefficient matrix. Now right side. Right side 7, -1, -4. 7, -1, -4. Okay. How to solve the linear system? Forward elimination, reduce the augmented matrix to epsilon form. Then backward elimination to further reduce epsilon form to reduce epsilon form. Okay. Now I skip the details. Skip the detail. Okay. 1, 0, -4/3. -1. 0, 1, 0. 2, 0, 0, 0, 0. Separate. Yeah. Reduce epsilon form. And in equations, the first row is x1 minus 4/3 x3 is equal to right hand side, -1. Second row, x2 is 2. Down row, 0 is 0. Yeah. Now determine basic variables and free variables. Pivot number. So x1 basic. Pivot number x2 basic. Low pivot number in the column x3 free. Okay, now general solution. The general solution is solve the linear system for basic variables in terms of free variables. First equation is -1 plus 4/3 x3. Second equation, x2 is equal to 2. Okay? Some people may say that low x3. No, you can view this as 0 times x3. Okay. Now, how about x3? Arbitrary. Yeah. This is all the solutions of the linear system. Okay. Answer to the first question. Solve linear system. Then, second question. Write the solution in vector form. Okay. In vector form. Okay, a new page. Okay. The unknown vector. Unknown vector has 3 entries. X1. Type this equation, the first equation in x1. -1 plus 4/3 x3. Then x2. Type the second equation in x2. 2 x3 keep x3. Okay. Okay, now let me split this vector into a sum. Okay. Okay. Coefficients, constants form a vector. -1, 2, 0. Then plus second vector associate with x3. So this is a 4, 3. Second entry has low x3. I can write it as 0 times x3. Then 1 times x3. Now take out x3 from the second vector. Then again. X3. 4, 3, 1. Okay. Now let me give names to these 2 vectors. Let me give a name. P. P means particular. Yeah, this vector actually is a solution of the linear system. How? X3 is a free variable. When I set x3 to 0, then I see P, this vector, is a solution of the linear system. So I use P. P means a particular solution. Okay. How about this vector? I think I have given a name to this vector because this example is a continuation of the previous example. In the previous example, I have named this vector. Let me see. This is a previous example. Yeah, I named this vector by V. Okay. 4, 3, 0, 1. This vector by V. Yeah. So this is V. Okay. So the general solution of the non-homogeneous linear system is a particular solution plus arbitrary variable times V. Can you see a relation between non-homogeneous linear system and the solution with homogeneous linear system? It turns out that solution of this guy is a particular solution plus solution of this guy. Yeah, this guy is the solution of this linear system. Yeah, from the previous example. Yeah. So every solution of non-homogeneous linear system is P plus a solution of this linear system. I will make a summary about this observation in the field later. Okay, not now. Let me finish to answer the other two questions. Okay, other two questions. Then describe the solution set graphically. Okay. Yeah. These are all the solutions. X3 arbitrary. Now let me plot. Okay. Think about imagine here is R3 here. Okay. Origin is here. 0, 0, 0. Okay. Vector P. Let me see. Vector P is -1, 2, 0. Maybe say assume. Yeah. This point is vector P. Or let me use arrow. Yeah. No. No. Let me draw P here. Vector P. Okay. This point is vector P. Upon an arrow and a vector, they are the same thing. Okay, vector P is here. Okay. How about vector V? Vector V, say vector V is here, for example. Okay, vector V is here. Yeah, this arrow, vector V. Let me shift this the point here. Okay, vector V. Okay. Okay. Now let me plot the solutions. Say first, set x3 to 0. It turns out that this point is a solution. So the graph, this point is in the graph. How about let me set x3 to 1. Then we get P plus B is a solution. P plus B, how to add two vectors, add the corresponding entries, or use parallelogram. Okay. Let me use parallelogram. Draw a parallelogram. Then the diagonal is P plus B. That means that this point, a vector and a point, same thing. So this point is in the graph of the solution. How about let me try? Try some. Say x3 is 1/2. That means that this is a solution. Then 1/2 V about here. 1/2 V. Yeah. 1/2 V. 1/2 V. Now, how to compute this sum parallelogram? Okay. P and 1/2 V. Span a parallelogram. Yeah. So yeah, the diagonal line is the sum. this point is a solution. So pick different values for x3. Then you will see all the points together actually is this line. Yeah, this line is the graph of the solution. The solution of non-homogeneous linear system. Okay. It is a line. Yeah, actually, this is a line. A line passing the point P. Yeah, passing this point. Okay. And is parallel to the arrow. Which arrow? Yeah, this arrow for beta V. Okay, yeah. This black line is the solution, the graph of the solution of non-homogeneous linear system. Recall that. How about homogeneous? How about the graph of the solution of this linear system? The graph we call from the previous example. The graph is, yeah, this line through the origin and parallel to vector V. Yeah. So the graph of this linear system and the graph of this linear system, they are parallel. They are parallel. Okay. They are parallel. I think this is all for today. In the next class, let me make a summary about the solution of non-homogeneous linear system and the solution of homogeneous linear system. There is a connection between these two solutions. The connection is solution of the non-homogeneous linear system is particular solution of the equation plus a solution of homogeneous equation. Yeah. Next class, I make this observation into a field.